My name is John Magyar. I'm a field application engineer with Altium based in the East Coast in our Boston area office. I've been with Altium about a decade and have quite enjoyed watching the tool evolve over the years. So I go back to release 6.7 when I started, and it's just amazing to see all of the development, particularly just in the last 5 years, I'd say, that's taken place. And I remember in the early days fielding questions, well, when are you guys going to do this? When are you guys going to do that? So a lot of what I'll be showing you is kind of the result of those new developments over the years that address those common concerns. So just by a quick show of hands, I'd like to get an idea of how many people are not using Flex today and are thinking about it. Okay. And so a few. And what about printed electronics? Has anybody even heard of printed electronics? Printed? So I'll be explaining that. We'll cover that. It's more of a additive process rather than a subtractive. And then we'll be talking about multi-module design, where you can merge many projects together under one parent project. And given that all three of these are fairly complex and take a few steps to go through, I won't be covering them in great detail, but from experience, I'll give you the essential detail that you would need to know, things to keep in mind if you're considering these technologies, and basically how things will flow if you want to implement any one of these particular applications. So with that, first I use the terminology non-standard design methods. So basically covering things that are not just a single project, a single board where everything is a traditional fabricated board and you place the parts and everything's done. I'll cover these three, rigid flex, multi-board design, and printed electronics in terms of, what are the demands that we've been getting over the years for handling situations that aren't easily accommodated by the regular PCB fabrication. So first we'll just kind of cover general categories of what this encompasses. So, when we have a standard stack-up traditional PCB, if that doesn't meet your design requirements, then you have to look for some type of alternative. Probably the best example, certainly the most popular, when circuits require some type of bendability or repetitive movement. And I'll get into the details of that. Common request years ago was, how do I encompass an entire set of boards so that I can generate board-to-board connectivity reports? How can I generate a common BOM? That was probably the one question I used to get quite a bit. And they want to source all their parts as one giant project. And I think that's probably one of the main reasons users have been asking for multi-module design. So that way it simplifies sourcing of parts. And then the third one is kind of a newer thing that we're seeing, particularly in one industry, which I'll talk about. It's a combination of lighting, LED lighting, and then some type of sensor electronics with that, controls, hand controls, touch capacitive sensing. And they want to skip the board altogether and kind of mold that into something solid shape and have all that conductivity in this printable, bendable, or solid form. So that's pretty interesting, and show you what we've done and an example of what that would be. And just in general, this relates back to flex requirements used in high vibration, high temperature, where you standard connectors and things like that wouldn't be applicable. So not sure if this is something you've encountered before, any one of these types, but certainly these are becoming more common in terms of requests for PCB design methods. So let's take a look first. Probably what I would say most folks are curious about would be rigid flex design. So some of the benefits, it eliminates the need for traditional connectors and traditional wire harnesses. So that alone is pretty valuable. You have the ability to improve your connectivity quality by not relying on physical connectors. You have something that runs actually through the actual board layers from one rigid board to another. So it's all one unit. This can save a lot of weight, mass, and space. Generally, this has been driven by military applications, but over the years we're finding it more and more in consumer electronics, and people are asking, how can I do that? How do I get started? What's involved? One more benefit, can withstand high vibration, high temperatures there. I don't have them listed, but a lot of users tend to say, well, rigid flex is going to be super expensive to do. And with some of the methods they have now, it's definitely going to be more expensive than a traditional board fabrication and assembly. However, there are guidelines where you can save, and if you go about it carefully, you can achieve a good result that won't break the bank or budget. I won't be getting into all those cost reasons and things like that in this presentation, but I have talked about that in the past, and we have worked with one of our sponsors here, Sierra Circuits. So if you see them and you're interested in flex, you can mention, hey, what's the average cost, and are there guidelines that can be followed so that you can reduce the risk and reduce the cost of the overall effort. So traditionally it's been more expensive, but there are ways to make that affordable. Some of the applications, mil-aero, medical, compact consumer electronics. So more and more today we're finding things like even a smartphone will have a lot of flex circuitry, wearables, medical devices, things like that. Another thing would be systems requiring high reliable repetitive movement. So if you think about things like printers, anything 3D, where you have servo motors or stepper motors driving things, and you need to maintain a good, reliable connection, and that's a place where you don't want traditional connectors. And things like compact space. So the phone is the greatest example. How to get something that's thinner and thinner every product introduction. Miniaturizing everything. So there it's a necessity that flex design is used. Okay. So then we'll take a look at an implementation overview. Again, I won't be getting into starting from a clean slate on any of this, but what I'll do is I'll hop through like the basic steps that you need to know and follow at a high level. So I'll be using examples that kind of lead from one step to another so that you get the idea of what's entailed. And it's something that you will let you decide if it's something you want to try and how to go about it, or encourage you to do so. So basically, we're going to look at how do you start? How do you get an outline of something that ends up compact with several folds and bends, and how do you even begin to think about an outline for that? How does that start? We'll look at what modifications we've made in Altium Designer to handle that. So if you think about rigid sections and then flexible sections, different stack ups. You're probably used to the traditional single board stack up, and how would you even describe flex that runs through all the rigid regions? And then bending lines. So how do we design and verify that something can make a bend at a certain angle or complete a certain bending radius? So traditionally, this has been an area where mechanical designers I've seen literally will cut out a stencil from some type of paper, fold it all out, and then practice with that to refine the ultimate shape that'll be used for creating the outline. So we have some nice capabilities that you don't have to resort to paper. You can use all of the 3D technology that you see in Altium Designer. And another big concern, placing components on flexible regions. That's desirable at times. Even embedding components into the flexible structure, that can be done. Altium Designer in general can handle embedded components quite well. So these are all things that you can achieve if needed for a demanding requirement. Another thing that comes up is how to handle cover lay definition. Sometimes the flexible portion needs to be a little more robust in terms of its covering. So instead of a thin Kapton layer, how to build that up and produce a more significant layer for wear and tear. So with that, what I'll do is hop into Altium Designer, and we'll go through some example sections and steps and show you how it's done. So I do have, minus my big monitor, so it may make this a little interesting, but I'll do my best here. So starting out, let's see if I can go full screen there. So this might be the starting point. Everybody can see that. I don't know if that's bleeding into the background, but we have a complex outline of what will be the flexible application. So basically, this is going to have one center rigid section and then these two wings, this left and right wing, that will be able to bend and move in some pretty complicated folding patterns. And then at the ends of each, there will be some electrical connectors at the end of the wings, and they'll need to be routed. So this is typically the starting point. You can get here from importing DXF or any type of outline method that you use. For simpler designs or simplistic, you can even set a snap grid pretty coarse at first, and then you can draw the complicated shapes with lines and arcs just interconnecting, and when you get one main outline, that's the goal. So either way, you can import this or draw it out manually. However you need to do it, your mechanical group is most likely going to define it. But what you want to do is simply drag, bring all this, and then go to the design menu. And under board shape, we can say define from selected objects. Ooh, sorry about that. Thanks for spotting that. There we go. Yeah, now we got the entire outline. So design board shape, define from selected objects. So doing just that will give us our shape. However, everything is still traditional board. If I go into 3D mode, you'll see that that's not flexible yet. So the question is, what do we need to do to make this flexible? So a few different things, and this is where the tool has improved quite a bit. I think this was introduced back in 2015. So I go back to 2D. And first we'll start with the Layer Stack Manager. So if you're starting from scratch, at this point, what you would want to do is build up your layer stack. And here we go. This part of the product has improved greatly over the years, and you'll notice up in the corner here, we have an option for rigid flex. Now with that set, what that enables us to do is define our, or any number of rigid stack-ups relative to a flex stack-up. So the assumption is that your flexible sections will most likely have minimal number of layers, like 3 or 4, where your regular board will have a traditional stack-up of dielectric and copper and so on, and then top solder mask and all that. So to accommodate the flex region, we can simply look at the thing. Well, the tool understands that the top layers are not going to be bendable. So right away it takes those out of the makeup of this particular stack-up. But you still have the option to check and uncheck certain ones and put those back. I have seen even more complex flex stack-ups where it can even be more than 2 layers, where they do a double band, and that's a little more tricky with the bending. But the idea is that each section will have its own layer stack-up. So for this board, we just need the 2, the rigid and the flex. For more complicated applications, you can define as many as you need. And one of the things that you want to do is very carefully go through, perhaps working with your fabricator, and choose the materials. And you'll see over in the properties panel the resulting selection. But a lot of folks may not realize this. We've added lists of commercially available materials, so pretty much by name. If you looked at these and went through with your fabricator, you can pick these out and choose one that's appropriate for your application. And it carries with it all of the parametric information, such as dielectric constant or thickness, anything else that's important. All of that information will be populated in the Layer Stack Manager. And there are even columns that you can display. So there are many more types of things that can be shown. But all of that information then lives in the layer stack-up. And the layer stack-up has actually been separated out from the board itself. It lives in the board, but it's its own editable object. And you can save to the PCB, and that means any updates made to it go into that board and live in that board. If you are using a data management method, one of the nice things you can do is you can make several board stack-ups, define them, and then store them in the server, so that as you need these layer stack-ups, you can simply check them out from the server and make them part of your project there. So that's the stack-up portion, and you'll notice up here under features, I enabled that from this menu. We also have printed electronics, which I'll be talking about. And there have been some enhancements for achieving back drilling if that's needed. I won't be going into that, but one of the newer capabilities, I remember getting hammered for that years ago. It's like, why can't you guys do back drilling? And now we can. That's tied to a DRC rule. And again, you set the layer information up in here for which layers actually get back drilled. So we'll be looking at the top two, printed electronics and now rigid flex. So we're working here. So now I have my stack up. I have my board outline. The next step is to make this flexible. So what I can do is show you a new mode. Some of you may have hit this by accident. If you know about the 3 key, that takes you into 3D. 2 gets you back to 2D. And if you ever accidentally hit 1 and you're wondering what this is what's referred to as board planning mode. So in this mode, you can change the size, shape of the board, but it's primarily been implemented for defining the rigid and flex sections for this particular type of application. Now, one of the things I'll do, I'll just zoom in here, and to create the divisions, if I want this to be my standard type of PCB, I need to define that as such. And to do that, what I'm going to need to do is go to the Design menu, and then I'm going to what's called Define a Split Line. Now these can be a little finicky to deal with, so I'll probably have to set the grid to a fairly fine grid, like 5 or 10 mils. We'll try it at that. And then what I want to do is grip these two corners here and set one of these split lines. So these can be a little finicky. They want to snap as far onto the edge of the board. And you'll know you see one when you see this blue dashed line. And they do snap to grids and objects primarily. So sometimes we have to, move them around. That setting this up on a super well-defined grid is important relative to the reference mark. And so that sets up one. So as soon as I do that, notice how when I click here, I've divided this outline into 2 divisions. I'll go ahead and set something up over here as well. These can be a little finicky depending where they want to snap or not snap. And this one's cooperating, so try to get that a little better. And generally for precision, you want to have this all perfectly on grid. So there's my division, and now I have a left and a right section. So if I double click in any one section, I get the properties, and I can define what type of layer stack up it gets. And this will be layer stack region 1, and I'll click OK. And then here, here's where I specify a name. So this could be the right flex. So I'll just give it a quick identifier. So if we do flex R, and I have to set the type so it knows it's a flex. If you're doing other types of design, you can use custom coverlays. Again, a more substantial covering on the flex section. And then there's locking 3D. I'll get into that later when we talk about animation. But we shouldn't really need it with this because this one's just a single center board. So now this is the rigid section, and then over here we have the other section. So I'll define that as flex, and that's the flex left. And that's generally what you would need at this point. So if you go back to 2D and then into 3, you can see the appearance changes already. And there's a notion of what we refer, if you're used to the PCB panel, that kind of general browser of all different types of information. I'll go in here. It's the stack up layer stack regions. And if you click on flex, it'll have both of these sections as flex sections, so it knows what they are. And then it's going to refer to what's called a bending line. So I'll go back to the board planning mode. And one of the key things that you'll have to define is referred to as a bending line. And these can be placed anywhere along the flexible section. So I might want one generally right around here. Naturally, this would have to be calculated precisely by your mechanical designer. But in the design menu, I'll just place one of these just to show you the effect of it. And define bending line. Similar to a split line, but a different function. You'll see it's a dashed yellow line. And as soon as I place that, these can be used creatively on different angles, so you can get things that spiral and all sorts of interesting folds. So that defines a bending line. And then we would want to give this what's referred to as a bending radius. So this is going to define how much of this will bend, and then you'll start to see an outline of how much area is affected by that. So if I want to bump this up by a factor of 10, that should give me a radius there. And then what we can do, let's see if that will bend for us. If I go into 2D mode, or actually 3D, we should have a line there. If this doesn't work, we have the other reference to use. Yeah, I'll do that with the more complete piece. But the idea is that as you have all these bending lines defined, actually, let me make one of these different, change the sequence of that. We can try this. So this should start bending, but I'll get to that. Let's go back to that. So that's back in the layer stack, or no, the properties here in 1. And then 3D lock, that gives it a bending reference. I think it might be something more than that. Let's see if that, yeah, there we go. So that starts to bend, and that's just a simple one bending line. And you know, you can look at this from different angles, and it helps, you know, much better than working with paper. So you can start to get your creation to do what it wants. We have a much more complicated set of bending lines. Too many to do, you know, in one sequence, but I'll just refer to this in the next design. So that's pretty much the bulk of getting to a rigid flex design. There can be any number of rigid sections. There's no limitation. Yeah.
Now, if you did this and everything is at rest flat, what
Yep.
if you had some parts that had to be like bent up, like for assembly? In other words, you're not going to bend it, you want it molded to be
So
an angle.
there is something referred to as a folded state, and you can put this into that folded state, and the best you can save that out as a 3D model in that state and work with like a physical verification to do that. But generally, because it has to be manufactured flat, you know, it can be bent and used however it's needed. So generally, There are two types of flex applications. What they call is a single, a one-time bend where they bend it all up just to get it into a certain configuration. And then the other ones are constant use where they're always moving in their application. They do have different types, and those are available in the layer stack up. So if we go back to that, you can get, for the rigid layers, notice that they're different for what we just probably have a default for the top. But the dielectric for the bendable, it's usually like a Kapton type, but they're all selectable from this list. And if you work with your fabricator, they'll provide guidance on that.
Some materials are one bend only and some are...
Well, they have different characteristics. If it's constant bending, you might use something, more substantial versus a one-time bend to get it into place. Question?
Yeah. So I'm just wondering, could you have like two bending lines kind of cross each other so you would have a point where you have like level 5 axes?
I've seen attempts at that. It doesn't. Sometimes it's not able to resolve the movement. But the more interesting thing I've seen is closely placed bending lines to get it, like a non-right angle. So if you need to make some special angle, but intersecting lines, I think it doesn't handle that well. So, because I have seen some people, they were making these squares out of flex, and it was all cut out in the center, and that wanted some type of, two-dimensional bending. Sounds like something similar, and we had a little trouble with that. So perhaps something I could revisit and look into. But. All right, so back to, what are the next steps? So we started with the board outline. The next thing we would want to do is more formally add the bending line. So I'll open a board that already has that bending lines defined. So this is just a continuation of this process. So it's the same outline and stack up and everything. And you'll notice on a mechanical layer, there's a bending line definition, there's 90 degrees, and there should be some radius information here as well. I'm not seeing that, but it's just saying bending line, 90 degree. So you can set the bending to be different angles. And then the other key thing is the bend radius. So we want to tell it how much of a bend to make given that bending line as a reference. So for that, we go back to the PCB panel and look at the layer stack regions. And again, this gives us all the definition on the flex as well as rigid regions in the design. And some of these can get complex. You can have, literally dozens of regions and more complex designs. But you can always get to each individual one and work with it. So if I select flex, it has the two, the left and the right. And what we can do is take a look at the different bending lines. So everywhere you see in this mechanical overlay is where a bending line should be. And those would be placed using the method I showed earlier. So if you do the design place bending line when you're in the board planing mode, just hit the 1 key. Then you'll see all the dashed lines, and you can see how they correlate to the markings on the mechanical. That's one method. It's kind of handy having a mechanical overlay to where these belong. And you'll see some of this in yellow indicating the actual bending radius. And the bending radius is defined over here. So for each one of these, as soon as I click, you give it an angle. It's either in this case plus 90 or minus 90, that determines the direction that it will flex in. And then you provide a bending radius. So that's how each bending line would be defined by going in here and specifying. And then you can see the region that that covers in terms of bending. So, so this is a pretty straightforward way to get the precise movement that you need through animation. Yep.
So, you mentioned that it's kind of a pain to find those split lines and defining the bend lines too.
Mm-hmm.
Is there any way to get this info to come in from the MCAD tool, or do you have a plan to do that?
You can, as long as it's done relative to a reference like this, you can import that in as a mechanical layer with those markings. So if I go back to this one, that may be how this one started. I didn't actually design this.
The split lines manually again.
Right.
And another thing that happens quite often is if you make, let's say you spend all the time doing the split lines and the bend lines, and then the mechanical person comes back and says, I need you to make this board just a little bit smaller.
That's true. So as soon as you do move one of these, it does. I've encountered that. I'm not sure if there were any plans to improve that to make it modifiable. The board planning mode in general has something where you can take an edge and extend it out. For regular boards.
But it happens all the time.
Yep.
Somebody will want that arm length, and you've got another rigid section at the end of it.
Yep.
Rip it all up and
Yeah.
move it.
So that's been, I know that's been requested as an enhancement.
We're
Yeah.
officially requesting more.
Okay. Okay. Yes.
If you enable, and you were placing the region borders, you didn't have the track arc vertices enabled as selected. You should have been able to pick up the ends of the straight sections.
So here,
When you're placing those blue region lines.
right, the blue split lines they're referred to. Right. Right there.
Yeah, you should have been able to pick up the ends of the straight section of the borders if you had all layers on, not just current layer. And
It'll find the mechanical, the endpoints of the object,
outline
and then it'll snap to that.
to that. And that should give you much more precise control.
True. So in that outline, if there's an endpoint, where the two points meet, and grid plays a little role in that. Sometimes you have to
Sometimes
adjust
you
it,
gotta turn the grid off
and
or
then
make it really large.
yeah,
So you
and then
don't
it,
get distracted by it.
it'll snap to that edge. So, but that's at this point. So the next thing would be to do is bring in the components, and that's just as it is with any other type of board. So to speed the process up, I'm just going to go into my projects, and I'm going to open up another board at this point. And let's see, just want to get this from the desktop here. And these should be here. 1 second, sorry about that. Last board to open, so it's a file open, not a project. And here we go. Here, components placed, just to speed things up a little bit. So that's going to be the exact same as it would be for any other type of PCB project. You're going to transfer the components from schematic into the board. And this particular design does not have anything placed on the rigid sections. You'll see in a minute, given its use, these are meant to freely move. But there are applications where you may want to put components on the flexible region. Surface mount components, of course, work best. But I have seen connectors actually at the end, which go through and are a permanent part of the flexible region. So this might be an example of that with some copper at the edging, and then that has to be routed out and making the connections. Not sure if you saw any of the advanced routing that Derek did earlier. One of the things you'll be able to do here, and I know this has traditionally been a problem where, okay, I got my flexible shape, now I want to start routing this. So if you go into the interactive route mode, start routing a pad, and that comes out, and it's probably complaining about some design rule of width or something, but I can use different arc modes. I'm working in 19, so if I do shift spacebar, I can start to get arcs, and if you're patient and careful, hit the backup key every now and then, you can get this to follow the contour of the shape. But in 20, we'll be able to precisely follow that board edge, and making this type of routing much more easier. That's definitely one of the most requested things I hear is, because a lot of time is spent just trying to make that one corner when you can drag multiple things around the corner at once, that would pick up the productivity of the routing. I'm not sure if Derek touched on that earlier, but that's one of the capabilities in 20, which is still in beta right now. Yep.
Question. We have a unique application where we need to actually coil the flex 2 or 3 times because it's going around the corner. There's a motor that's going to spin
Okay.
360 degrees,
Mm-hmm.
and we want the flex to coil in and coil out as it rotates.
Okay.
How would you coil it up here 2 or 3 times and get the proper length?
This is similar. I'll show you this in 3D, so I'll do that next. Just to finish up on routing, same as it always is with any type of routing. The rules are active and everything, so you finish the connections. But if we go into 3D mode, and if I back out, so in this design, the bending lines have been placed with that in mind, that type of movement, using negative angles and positive angles, and then controlling the bending radius. We'll go back to the PCB panel, and this gets interesting with what's called the fold state. So here, everything is flat, and as I move this, this has been designed to do something similar to what you described, I believe. Something like this, maybe? More of a complete wrap.
Yeah.
Yep.
Like 2 or 360 reps.
Okay. Certainly achievable, and that would be handled, let's see, right back in here, layer stack region. So I would go to the flex, and my first instinct would be that instead of changing angles, just continuations of the same direction, that could wrap and work with the bending radius so that you have some.
Having more bend lines a lot closer together.
Yep.
And then it would wrap upon itself.
Yep.
Would it do that?
Sure. There's nothing. All that is just the number of bend lines and the length, of course. So that has to be calculated out somewhat at first, and then you can achieve that. Yep.
Your distance between the bend lines continually descending, maybe like a 90 or 180.
Yep.
And put that out, but I think that I've done this old-fashioned way, and yeah, I mean you can only get so far with population. I mean with the it's just the same. Whether you're throwing it on the tabletop
model it and animate it and verify. So, but certainly should be possible. I've seen things, do some interesting, wraps and twists and non-standard angles and things like that. So, yeah.
So when you're drawing the bend lines, what kind of like keep outs or DRC rule things can you do there, especially if you're like dropping components near that region? Is there anything that will protect you from trying to put things where bends are at?
Right. You might want to, you could place a regional keep out. So when you place a region these days, I think it has a property to be listed as a layer specific keep out. Or you could have all layers. So I could take a look at that real quick. I think if we just do like a place region or fill solid region, just draw something out real quick. In the properties over here, I know we've updated this. There's a concept of making a keep out, or there might even be a keep out object that you can place. Yeah, let's see here. You can make these. I'm sorry?
You had kind up there and said copper. Isn't that very selected for keep out?
Let's see, back here, place.
No, if you select the shape, you place down first, the other shape.
Oh, this one.
Yeah, and if you go down, then it says kind.
Oh, right. There we go. Well, that's board cutout, polygon cutout, so that'll handle cutouts. But the keep out, I believe, is its own object now. I think somewhere around 18 that may have changed. And you can actually do place keep out. So it's not limited to just a line, board outline or keep out object. You can place the shapes and then give them the keep out property. So you can do that on the flexible regions to control that a little better. And that's at this point. Let's see, the other thing you can do, you can put this into a folded state, and then you can export. If you want to send this to the MCAD folks, I believe Parasolid will handle folded state as well as step models. So if you do saves, it'll export this file out, and then your mechanical designer can import that into SolidWorks and use that. One of the things we are working on is a more direct integration with SolidWorks. We have that really well now for traditional boards, but in the future that should be included to handle flex boards as well, rigid flex. Because the same thing happens as soon as it goes into the SolidWorks, it loses that flex definition. So they're going to try to accommodate that pretty soon. Okay. Now, is anybody encouraged now to give it a try? So, question?
I noticed you use the middle layers for your flex circuits.
Sorry. So,
I noticed you use the middle layers for your flex circuits.
Mhm.
Is there some rule of thumb on where, how many, and obviously you want them to be in the middle, or is that just my supposition?
your fabricator would probably have the best guidelines. They're the ones that are responsible for, manufacturing it, and they definitely have quite a few rules. We don't yet have design rules specific for flex, but they have general guidelines and documents that holes can only be a certain size, down to a certain limit, and then you have to have a certain ratio of diameter to the hole size. Probably a good 10 or 15 rules like that how close a via can be to a bending line. So if you do talk to the fabricator, they probably have a document ready that they can share. And if you see the Sierra folks here this week, you can mention that, because we've partnered and done presentations like that where they give us all that information. I should have brought some of that, but they have a document we probably access online. And in the back, sorry.
My question was, how do you add different sections to the flex?
I'm sorry?
Different sections to the flex?
That was going to be my question as well.
Additional Kapton or?
So the still a flexible portion, but have different composition in terms of the stack up. You can, I haven't tried it, but you could probably have two flex sections next to each other as long as the layers are continuous. Let me just check that out real quick. If I go to Design, Layer Stack Manager, and so let's say we have the flex region. We can go add yet another. So this can be a flex. So now we have 3. You can change, let's see. You would have to add them. These, yeah. We go back, let's see, back to board planning mode. Let's take a look here. I'll go back to the board outline. In this case, when you select a section, let me do this in, there's custom cover lays. So you can get an additional layer on top of the copper. So, oh, stiffeners, things like stiffener, that's more of a challenge. We hear that a lot. Do you support stiffeners for flex?
You can have two dielectrics together. You put one as an adhesive and one as your stiffener piece. Two dielectric layers in your stack up.
The one thing, we don't have a way currently to show an outline of a stiffener and then have its material and everything. We're pretty close, but it's not there yet. Generally, that can be added as a fabrication note. And 3D models, I have heard people will add as a component, because that's generally what it's used for, to add some resilience to the flex in component areas, and that has helped out. But yeah, that's one thing we're still need to develop. Question?
So following up kind of on the flex question.
Yep.
This is just more of a note for the future. If there could be some way to add custom layers which can stack up specifically where you want them. Because right now there's kind of rules that what layer can be inserted at what location in the stack up. And that would really help out with, let's say we have 2 stiffener layers and we add it to the bottom. It's kind of hard to get those custom layers exactly where you need them in the stack up. The workaround we have to do is we have to change like the solder mask layer and just rename it stiffeners.
Right. Do you use cover lay? So custom cover lay can be added, but that generally covers the entire flex section. Not cover lays. It's a one-time surface layer. Right. So.
Yeah, one more thing I was going to touch on is the components on the internal. So we actually put chips down and put cover layers over those too.
Yep.
You need to have the ability to put those components.
Mm-hmm. So I was actually thinking about an example that I created last year when I was talking to somebody about flex. It is possible. There is a construct referred to as a cavity, and I'm not. Let's see. It would be in. I think it might even be in the component definition, but you can add. It's its own object. and it'll have dimensions, so it'll be a cavity, and you give it a start layer, a stop layer. And I had a great example because someone, it was actually a year ago, but you can have them top facing or bottom facing. So that's another thing in the stack up. You have the ability to orient, you'll see in here, this, there should be, it's not actually in here, maybe it's on the Flex one. There should be a column that says component orientation, so naturally on your top surface layer, that's going to be top. On the bottom, it's definitely bottom, but in the middle layers, you could direct it either direction. And then you can tie a cavity into that, so like small, terminating resistors, things like that can be embedded directly into the flex, and then you can control the thickness in the layer stack up of the flex. So certainly all possible there. But yeah, the stiffener, that's one that's on the list for quite a while. Yeah.
If you're doing rigid with flexible rigid,
Yep.
do you have a different stack up on each of these areas, or do you have to do the same stack?
I believe the copper layer has to go through. So we used to have a different representation of this where it showed them all side by side. And generally the copper runs through. And, but I know for dielectrics, you can have them limit over the boundary, have it overlap by a certain amount. So things like cover lay, that's certainly adjustable. But I haven't tried it with the actual copper. But someone said it may be possible. You've done it?
Yes.
Okay.
You can have like an 8-layer rigid and then like a 4-layer rigid on the other side. It's totally fine. As long
And it's not one continuous?
as your flex copper goes all the way through.
Oh, yeah. Oh, sure. That's what I meant.
These would be different things.
Right, the dielectrics. The dielectrics can be, in fact, that's one of the columns. They have a term for that. Pullback. So you can, I think it's cover lay pullback, like how much it goes into the solid section. Usually it's a minuscule amount, but just so they have some binding on it. But that is possible. Okay. So something you want to go home and try. I actually did one of these when the new features come out. I like to understand how they work, and this was a pretty cool one. So actually made one of these that's got a few different rigid sections, and it's used for sensing temperature. Very simplistic design, but going through the process, it's it's good to see all the different steps. So we have 2 more items to cover. We're doing fairly well on time. The next one is I'm going to connect to a server because the design is fairly large. So I just want to queue that up and close this out. So before I close this out, any other questions on the rigid flex? So as long as you understand it better, have a better idea, then that's good.
One more question back here.
Sure.
So sometimes we want to expose like a copper layer that's several layers down.
Mm-hmm.
So is there, I didn't see a function for like a cutout that goes to only certain distance, it kind of goes all the way through.
Probably the cavity would be the best for that. I know it's on this PC. I'll try to find it. Maybe I got another presentation after this, but I'll try to find it. So cavity is the object you got to look into, and that'll help you with components, embedded components, and then any kind of opening that extends through. All right. So we'll just close this up, and I'll queue up the next. This is really more of a project, and I won't be going into as much detail with it, but I'll just show you the key pieces and describe the process. So fairly often we were asked, how do we do one continuous bill of materials for 27 boards in a system? So I'm going to connect to my server to do this, because this is where I have a large design. And by server, I mean data management server. Ooh. Let's see, should be able to get there. And I'm going to bring up a particular project that it's very intricate and complex, but represents ideally, the reason why you might want to try this method. So if I go ahead and open a project, now connected to the server, this is data management at its best. You don't lose stuff and it all stays together. I'm going to open up what's referred to as a multi-board project. So all these other projects you see are tied together. And this takes a while to open up. And I want to queue this up, and then I'll hop back into the presentation and we'll talk a little bit about it. And to get the full 3D rendering of it takes a little bit of time, so I'll let that load. But basically, within a multi-board project, you can reference existing lower-level projects. These exist as independent entities, so these projects that you do them as you normally do, but there's a way to create an a top-level project that will access all of this information and then electrically tie it all together, and then it will give you the bill of materials for sourcing as well. So with that, let me just open up the two assemblies, and then we can talk about it. So defining a project, and then this would have a schematic representation, and I'll explain how all of these different blocks get tied together. And then the more fascinating one is the full 3D assembly.
Are these examples available on
Sure, this should be freely available. If you have a thumb drive, I could download this, but I think we do have it online. If you ever do an evaluation of one of the data management servers, it's included in that. So if you might be asked about Concord Pro, having a look, we have a really convenient online eval, and that's part of that. But I could download this and provide it on a thumb drive if you wanted to take a look. So this is still opening, and I'll let it do that because it's going to take a while. There it is. All right. So you can see the projects over here on the left, and I'll just cover some of the presentation. 1 second, and we'll talk about, we'll go through this one. Whoops, oh, geez. Wrong meeting, sorry. Hang on. I had another one. No, here we go. A lot going on today. Multi-board design. So let me put this in presentation mode. And here we go. Okay. So for multi-board, the real benefit here is that you can collect together multiple projects that were designed at a lower level, and then have one top-level project from which you can generate documents, primarily bill of materials and other common information, and then you can do the 3D assembly. So there's two parts to it. There's the schematic representation, which is pretty neat, and there are a lot of benefits to doing that. One thing that I like this for, and my early days as an engineer, I designed this great multi-connector system, but what I didn't realize is two of the connectors were symmetrically reversed, and all the pins were swapped. And found that out in the lab, but something like this would correct, or you build correct by construction. If you do this method, you can build up so that all of your signaling is verified as you create this top level project. So that would have been nice to have years ago. But you can navigate through the system, and I'd love to get into some of the detail, but it gets to be quite a bit. But you can actually take signals and you can make changes either at the lower level project or higher level project, and then push them in the opposite direction. So signal modifications. So, results in primarily better sourcing of your materials. It gives you that 3D assembly, and it helps verify the system level interconnectivity, which is something that that can be tough if you're just doing that separately in another tool. So backplane.
Mechanical integrity as well.
Yep. So you can fit and see everything, and documentation, critical process if you want everything locally packaged up and archived. This is one way of handling that. And again, the interconnectivity verification. And as I showed you the example, we have our embedded systems, small, multi-board. Each board has a different function, and it all ties together at the system level. So that's what we'll look at next, enabling the 3D, and I'll show you the BOM and stuff. So let's step through this. Kind of tough to do everything over, but we'll start with the schematic. So the first thing you need is to create one of these multi-board projects. And that's just the same as creating any other project. You just say File, New, and then you'll see there should be multi-board project here from under the project menu. I won't do that because it creates another one that I'm not ready to check into the server. But then within that, you have this block level diagram, which I'll show in more detail. And then you have the mechanical assembly. So, very similar to a PCB project where you have the logical representation and then the physical representation of everything. And then there's naturally a tie-in to both. So really what it starts out as when you have a blank slate, you can create these blocks. You go place. Where's this? You place a module within here. So you start out with just a simple block. And then in the properties panel, if I double click on this, I can give it a name. So it'll have its designation. So this could be like PCB 10 or 12. I don't want to conflict with anything. And then can have a title. And then you can use the pull down to reference existing projects and a new one. So if you can use the navigator to go find something that may be outside, not under server control there. So just a way to do that. So I'm going to pull in one of these existing ones here, even though it's duplicated already. You can do that. You can make multiple items. It's not letting me do that. So it's in use. Maybe I can try to pull in. But that one's, I got other stuff that's part of one as well. But the idea is that once you set this, you tell it what module this block represents, then it knows all about the connectivity, and I can show you that from one of the others. So that's how you would start. You associate it with an existing project, and then it will inherit that information. And what it looks like is simply this. If I click on this one, I can go in here and see the connectivity. So if we go in, and there's a way to get at all of the individual detail as well. Don't want to, but we should be able to split these out and see the individual signaling from within the interconnects. Actually, there's a different way to do that. So taking a step back, one of the things that's required to form this interconnectivity, so here's where the interconnectivity happens. Now we'll look at the properties. And this is what I was looking for. So here, this shows me for this module, every signal, every pin that's in this project, and then what it's going to mate to on the other side. So you get this detail all listed out and verified. So that's by clicking on, these are referred to as entry points. And that's where you can do the swapping as well. So placing a connector, I'll do that in this case. I can just delete this one. And what I can show you is in one of the example projects, I'll try to pick something that's pretty tiny. I think it's this one here. We'll look at a schematic. And in the schematic, it will have a connector. So for doing this, to implement this, all you need to do is go into every component that has the connector. Let me bring that components properties back. Here we go. And in the properties of that connector, when I select that, the parameters, you'll see one that says system. And if I define it as a connector, that's what's going to make available this I/O. So anything from an edge connector to any type of formal connector that you've designed into the board, once you expose that as a system connector, that enables this interconnect. So with that in all of your lower level projects, for every connector, simply define that parameter. You could probably even do that globally. And once you have that information, whoops, we go back to the schematic. Each component will create one of these. This is referred to as an entry. And a lot of people ask, is there an option to show explicitly every pin? And unfortunately, I'm not aware of a way to do that with the wiring. But you can certainly get at all of the information from the properties panel. So if I bring that up, I think that's done for simplicity because literally you could get thousands and thousands of signals intersecting, and it's not, we don't want to get into multi-sheet construction and everything because it would simply be too complicated there. So you can get at everything here, what something's made it to, and you can actually, for some of these that do have connections, you're right, sorry. So I'll make that connection again. Once that's connected, two things. You'll see everything in that lower level dialog, and then there's something referred to as the connection manager where you can do swapping. So I'll go ahead and place a direct connection. And same as schematic, you just want to make sure you start and connect at the hotspot there. And then these directions can even be changed in the properties now if I do that. So it's taking that predefined system information, system connector, and now that I have that, when I split these out, this will show the mated connection from both sides. And with that, the design, there's a connection manager. So here is where I can start to make changes. I haven't really run into this in a while, but what this will do is check for conflicts. So if you took the example I gave you where you have things twisted around symmetrically and there's a conflict, it can spot things like that, and then you can manually make changes and drive that into the lower level projects. A couple questions, I think you were first. So it's one electrical connection. So this, the other one,
So CM1 and CM3 has to be the same thing?
nope, they could be different. So it's, you can change that in the connection manager itself. So when you define this general connection, you have some flexibility in terms of the properties. There's something referred to as, well, that would be set up in the entity. You can split out a sequence so it doesn't have to follow, one right after the other. But you can change these to mate with different connectors, and you may have to do that manually at certain points. And again, I think that's done with the connection manager from here. Repeat the question. I heard you say. A common question. You really couldn't design a wire harness with it because it tends to keep a lot of the detail internal. Usually for wiring harness, you want to see things like wire gauge and attributes of the wire as if it were a part. Yeah, and it doesn't have that, but what it does do very well is verify, validate the electrical continuity, and gives you the opportunity to make changes. So you can change the from to in here. Trust me, it's doable. You can move the column information around, and then that will force a new configuration. And you can establish that at the top. You can also push changes down to lower level modules as well and make changes out.
But that just simply makes the two modules match. It doesn't actually, if they don't match, pin one is one thing, pin two is another. It points that out, but it doesn't actually, you still have to get the end result of the two boards that are being the same.
Right, you have to verify that the connections are such as you want them. Yep. Hand in the back.
So I have a question about the interconnects. Is there a way to just have it to where the interconnect is a copper on copper, like two things on copper, or is that?
Sure, as long as they have a pin ID. So if there's a notion of a pin, that should be doable. So there's a notion of a wire, a physical connection, and then there's direct connection assumes like a pin in a socket type of connection where there's no device, it's just making the contact. So that can be represented. So, yeah. Oh, sorry.
I know that, I think it was towards the beginning of 19 when we started using multi-board. We had different variants that had different pin names. So, say the motherboard had a certain pin on it with certain names, but they could be swapped between, say, a signal and that return. And then each of the daughter boards that would plug in, if they had a different variant, would have different pin names. And we were having trouble getting those boards that could come into the multi-board viewer. Has that been addressed?
Things did get better in 19, and I think there are a few enhancements on the way. I remember it being very difficult at first when it was first introduced.
They have to match exactly, and it's not how we do.
Right. You need the variability to be able to switch things around. So,
I noticed in here, in this example, everything matches.
by name, but you can move stuff around. You can do swaps, and
Not necessarily that we're only do swaps, but we want to be able to
have it understand.
Like a TX to DX.
Right.
What it is and the in-between does connect.
Yeah. I'm not sure if anything can be done with parameters, assigning parameters that would do anything like that, but Something I could check into if you're around the show, and I'll ask around. There are a few experts on this topic. So,
Or a table that correlates this signal name can connect to that signal name.
yeah, that should be handled in the connection manager. Show changes only, report, clipboard. I know they can be changed here, rename, but they'll have to, right. I'm pretty sure you can move things around here, the connectivity, but it could be a lot of work if the naming is such that, there's no pattern to it. So simple pin swaps are easy, but I can ask around, see if there's any plans. I think in 20 they have some changes slated. Yeah.
Is there any way to say that it's a board-to-board connection, so you can't swap pins anymore? Obviously, you can't pin 2 or pin 3 when you're board-to-board.
Right.
Either you need pin 2 or pin 2.
So locking,
Yeah.
some kind of, I'm not aware there might be some way to lock that down. So
When you have a rigid flex and you start moving, all of a sudden this guy has to be inverted. So
right,
pin 1 goes to pin 50.
right.
Instead of pin 1 goes to pin 1. Pretty cool way to check that.
So, but, okay. We'll take a look at the last topic, which is printed electronics. And this is pretty interesting. It's new. And at first, when people heard about it, they were like, who would ever use that? So I can explain it. Actually did some digging into this and found out where the demand is actually coming from. And let me see here. So if I get my presentation back. I wasn't going to go into that, but it's certainly possible. There's an axis where you can move things around, and then there's it's a little intricate. You got to spend a little time with it to line everything up. But there are alignment commands to reference points and things like that.
A
And
lot better than it was in 18.
sure, and they're hopefully improving that in 20 as well. But you can get things to align based on reference points and alignment and lock them. So let me roll back here. Printed electronics. The benefits, and again, this is pretty new. We integrate conductive components and lighting into a solid shape. And it's an additive process, so it's not the traditional etched board manufacture or fabrication process. And basically getting a lot of use in the automotive industry, and that's what's been driving this. So the traditional PCB does very well. Copper is highly conductive. The process has been perfected, and we can keep up with advances in high-speed electronics with copper. But where it's gaining, printed electronics is gaining traction is in the automotive industry, particularly for lighting, and then interior components within the automobile cabin. So it can be used for external lighting, and generally this uses some type of conductive ink. So again, it's not a traditional copper process. You're actually adding conductive inks, layering them up, and then that gets fabricated. And it can be fabricated in terms of a contour. So some really neat examples that I've seen would be naturally interior and exterior LED lighting. So taillights, headlights, running lights, interior lights, very common now in automotive. And they can actually build these into like an armrest. And that's one of the examples that I have here. It's something that goes in a center console and maybe a volume control or something. But they have these touch sensors that use your natural capacitive coupling, and you can use touch controls to dim the cabin lighting and things like that. So that's really where it's gaining popularity. And if you think about it, that works well in that application because you don't have to worry about high impedance or anything or high speed design. Conductive inks can be layered pretty heavily in something like that, and it's a perfect application. So we'll take a quick look at what this looks like. And again, it's a very non-standard approach, but certainly we can do it. We can create all the design files. For fabrication, particularly the 3D solid shape, there's a company referred to as Tactotech, and they're doing a lot of fabrication on this side. So basically, if you hand them all of the electrical and all of the mechanical, they can merge it into that armrest with touch controls in it, or a molded taillight that's a solid object. There are other companies that I'm aware of that do more of a traditional PCB board shape with conductive inks. But I think some of the drawbacks there naturally for high-speed design, conductive inks may not be able to compete with copper just yet. Maybe they'll get there. But if they do, we'll take a look at how to implement something like this. So the key thing is it's an additive process, which I found pretty neat when I first looked at this. So we'll open up a project that has one of these. This is going to be outside my server. And this should be right here and here. So we'll take a look at a PCB document, and I'll explain how it's constructed. So this odd pattern that you see is pretty standard. We've actually had pattern generators to do that a while ago, going back probably 10 years, where that's pretty typical for touch sensor control, where you have these strange polygonal shapes, and they're all tied together. And basically, as you run your finger along that, the natural capacitance provides signaling to a controller that can then take some action. So let's say you want to dim lighting, control the volume, any type of thing like that. One of these sensors fits the bill pretty well. But that has to be close to the surface of whatever the object is. I think generally it can go through glass and plastic, a millimeter or two. And in this case, what it is, if we look closely, you'll see a ring of LEDs around the outer edge. So as you move this thing around, it indicates the level that the control is set to. And then there's some type of connection here to external of the part. Now, what this has is a very unique type of stack up. So if I go to the Layer Stack Manager, and you'll see that there's no solder mask, none of the traditional type of stuff. There's a bottom layer, a top layer. I suppose you can do multiple layers so you can build this up. But there's this notion of what's called an isolation layer. And it's not applied like a typical board stack up. It just means that you can use isolation where needed. That way you end up with this very compact, flat implementation. You could probably even do that thinner than a traditional board. And I'll show you what's neat about that. So this has its own library of different materials. If you look in here, you'll see names of materials, and I think there are probably selection. There should be a library type thing. There should be a pull down. I'd have to check into that. But this is, again, special material for isolation. Notice it's not saying dielectric layer. So when we get back to the board, what we have is a layout for top layer, bottom layer. And the interesting thing is, these are two layers without anything in between, and that's how you would design the layout. These are not really vias per se, because they will naturally, if they're lined up on that dot, it's a via object that we use to kind of anchor the tie-in of the two tracks together. So I have one on the top layer and one on the bottom layer. Now, this right here with the two crossing, technically, right now, that is a short, so that's flat. These are two layers meant to be stacked on top of each other or printed on top of each other. So the real interesting thing here is to work this to get that isolation layer where needed. We would go into the Tools menu, and there should be Printed Electronics. This is a free extension, so if this is something you want to try out, you go to the Extensions page, and you load up, I believe it's called the Isolation, I could show you that in a second, the Isolation Pattern Generator. And when you click on this, what this will do is look at all of the crossing points where there's a natural short, and then you can determine what you want to do. So we'll generate isolation, so it'll let you pick the layer, so isolation, and we pick above or where that isolation is going to go. So we pick the top and bottom layer in this case. And then we can make the shapes. There's an auto and a manual. I haven't tried the manual, but for using auto, it's going to fill those where those shorts are, but it's going to do it for everything. So we hit apply and OK. And now if I go back, you'll see that there's this isolation object added to prevent any of the shorting. So then all of this information gets transferred to the fabricator of this new type of process, and that's how they can layer this with a printed, 3D printed technology without having a full dielectric layer. Yep.
Is that top layer going to be a silver typically?
A what?
Is that top layer going to be blue line? Is that going to be printed with silver?
A conductive ink. Yep.
Got more about silver migration.
That I'm not too familiar with the materials that they're using.
Use things like alternate polarities so you don't get silver.
Yep.
Light through the layer.
Through chemistry, I know the conductive inks. That's a pretty new field. They are probably developing that, but I believe they have it perfected to a level which is, it's certainly catching on in automotive. So they're running with this. We have a lot of interest in automotive applications, again, for lighting and then within the interior. Now, to hand this off to a fabricator, let's look at 3D. You can kind of see, everything is isolated, that stuff, but this becomes very flat. So it's a very nice, compact way to design something. Automotive, typically not sensitive to high-speed concerns, so it works pretty well there. And then furthermore, this can be contoured, and this is the part we don't provide in the tool, but if you work with Tactotech, they can mold this into a solid shape when that conductor will have contour to it, but you've designed it from this perspective, and you can hand out, they seem to take regular Gerber, and they run with that to fabricate. Question?
Yeah, what's the logic in the isolation only being where you need it as opposed to the entire?
From a printed additive process perspective, it's going to save a lot of material. So if you think about it, that has to be put on line by line. And 3D printing, it generally is pretty slow. It's a lot faster for industrial machines, but they can save on material. They don't have to, put that uniformly. They can just put it where needed, and then that results in a cheaper, thinner collection of conductors. I'm sorry, Dean?
So when this comes out, there'll be slight bulges in those regions?
Yeah, there's some thickness to that according to the layer stack up. But that makes it flexible as well. So when you take out that layer, then it can have contour, so you can put stuff in armrests and things like that. Yeah.
So what's sort of like around the perimeter, you have components sort of small, probably already.
Yeah. Right.
And so are there special rules for, you couldn't use solder paste, solder, so is that conductive epoxy, and are there special rules?
Not sure, because it's a different type of process. I don't think it would be the traditional assembly. Not sure if Tactotech is here this year, but if you look them up online, they have a really nice overview of everything they provide, and they handle the service all the way through fabrication and assembly. So I think they probably do have special requirements for the type of inks that are used. It definitely wouldn't be the same as the copper that we're used to.
Any idea how you connect around that?
Connector, adding connector. Right, they do have edge, fingers like a traditional, and looks like that can be soldered on, so there could be some physical connector, and then maybe that ties into a flex of some sort that again is a pretty low profile. So, yep. Well, it's flexible to give it the shape, but then it becomes a solid object. The best examples I saw was an armrest from a car that had, I should have included a photo of it, where, right where your hands are, they have the various controls so that the armrest is solid. It may flex a little bit, but generally, to do something like that, you can only do that without that dielectric full layer. So you have these isolators where needed, and that gives you a little bit of play in terms of the ability to mold it and form the solid shape. Yeah, there's a photo of it. I can try to find that real quick. That's yep. Let me bring that up. 1 second. What's going on? All right, here we go. Here we go. TEK. I believe they were here last year, smart molded structures. So that's what they're, see, they have some pretty extreme twists here, but it shows how the technology can be used to do that. And yeah, right here, so. Formed. Yeah, this is probably a center console type of controller, where it might do multiple things like volume and switching and stuff like that. So. So I think they have a video somewhere here as well. Oh, right here? Okay. Oh, there we go. All right. Getting started. So yeah, here we go. So for instance, it might be controlling lighting, hit another button, a sensor button, and then that controller could be controlling sound or something. So center console, and then, you know, it has the contour shape. And then here's the armrest example right here, where just touches in an area are enough to control the movement of, you know, the typical seat controls, which was once a physical switch. So you're replacing things that are physical that could fail with something that's more durable and less susceptible to mechanical failure. So, okay. So that about wraps it up. And again, it's the theme has been non-standard approaches to design. So thinking beyond that, you know, simple square PCB and getting into some more challenging designs and enabling you to do more creative type of stuff or more complex stuff. Okay. Thank you all for joining. Thanks.